So in this video, what I want to do is just kind of summarize these two ways of calculating average rate of change that we're talking about, and that we're moving away from this calculation of average rate of change and trying to get to this difference quotient idea. But at the base of everything, they're doing the same thing. It's just with difference quotient, we're thinking about it a little bit differently so that then we can talk about it in a calculus context. So, our two formulas. Average rate of change, that's the idea that if we have some function, say I have a parabola like this, we can look at two coordinates, say a and then an output of f of a, and then b, f of b, and we're looking at the line that's created between those 2 points, which is our secant line, and the slope of that secant line is our average rate of change. So it's the same exact idea with difference quotient, but there's kind of this added element of where we have these two coordinates, we're thinking more about the distance they are away from each other. And with that, we want to think about what happens as we close that distance. So we have this distance between them, which is h. So with average rate of change, our two coordinates that we're looking at are a, f of a, and then b, f of b. And then for a difference quotient, it's that we have a coordinate x, f of x, and then we have a second coordinate that's a distance of h away. So our x coordinate would now be an x plus h, and then our output would be f of x plus h. So still the same idea of two coordinates, but then we want to evaluate what happens as h approaches 0. So again, this difference quotient, it's the same calculation as average rate of change, and technically in that denominator we're starting with our input of x plus h minus our input of x. It just ends up simplifying down to just h there. So let's take these two ideas and apply them to this application and see how these pieces come through and how these two calculations are interchangeable with each other. But it just takes a little change in our thinking to use the difference quotient, but then we can see how that's applied. Okay, so we have a population of bees. They're happily residing in someone's backyard a few years ago. Unfortunately, the population died off before the year's end, and we're going to let b of t be the number of bees in thousands, t months after July 1st, 2011. So our function is 32 minus 2t squared. It was not a constant rate. This is a quadratic. And we want to talk about the average rate of change at which that population decreased. So first off, from the time the bees hit their peak, so that's going to be when t equals 0, starting at the peak, to when they had officially died off, what was the average rate of change in the size of the bee population? And we're going to write a sentence for that. So we're starting at the peak, so when t is 0, so that's like looking at if we plug in 0 for b, that's 32 minus 2 times 0 squared, so 32. So there's one of our coordinates. That would be at the peak, input of 0, output of 32. And then when they officially died off, so that's going to be where we want to solve where the population is equal to 0. So we need to do a little work here. So that's going to be solving 0 equals 32 minus 2t squared. And then solving for t, so 2t squared equals 32, so t squared is 16. Square root of both sides, and we would have t equals plus or minus 4. Although this is a word problem, so we're just going to use just the positive. So we would have a coordinate where t is 4 and our population is 0. So there's our two coordinates that we're working with. So the average rate of change across those 2 points, we would take the difference in the output. So we could go 0 minus 32, the difference in those y coordinates, and I just need to keep the same order. So it would go 4 minus 0. So that's going to be a negative 8. So let's see, we started in July, so 4 months later, so August would be 1, September would be 2, October would be 3, so November would be 4. So with that, between July and November, on average, the bee population decreased by 8,000 bees per month. So we have a rate of change here of bees per month. It's decreasing because it came out to be negative. And then with these average rate of change, we just want to make sure that we mention that this rate of change is on average across this interval. So that right there, average rate of change question, application of that. So now what we're going to do is get some notation going. So we're going to write and fully simplify the formula for the average rate of change for our function over the interval t0 to t1. So what if we had two arbitrary times that we're working with? So with that, we're just plugging in our notation. So for b of t1, so that would look like 32 minus 2t1 squared. And then I'm going to go ahead and throw parentheses here just to help with the simplifying. Then we're going to subtract, and then if we plug in t0, so 32 minus 2 t0 squared, and then all of this over t1 minus t0. And now what we're going to do is just simplify algebraically. We're going to get a little algebra review here, but part of the work that we're going to be doing in this course is taking something that's like this setup and simplifying to a simpler form of that equation. So what that would look like, 32 minus 2t1 squared, we can just drop those parentheses. Over here we need to distribute in that negative, so that would be minus 32 plus 2t0 squared over t1 minus t0. In the numerator here we have a 32 minus 32, so those are just going to turn into a 0. I'm seeing a common factor of, let's go ahead and factor out a negative 2. So what that would look like is if I bring a negative 2 out front, then I would have t1 squared minus t0 squared all over t1 minus t0. And now in here with the squares, I'm going to use a factoring method, difference of squares. Not to go too long with this, but a lot of this course is bringing back algebra knowledge and some pre-calculus knowledge as well, but things like factoring. And what I'm going to try to do as much as possible is call out what the methods are so that you can go and look them up and get a refresher on them. I'll even try to link to them outside of these videos so that you can go and refresh as necessary, because a lot of this course is needing refreshers so that we can move through the calculus. So difference of squares is what I'm using here because we have a variable squared minus another variable squared. So in factoring that, what it would look like is I would still have that negative 2 out front. Then I can factor into two pieces where I have the addition of t1, t0, and then multiplied with the subtraction of t1, t0. So there's my factored form. And now that's perfect because I can see I have this matching in the denominator and numerator t1 minus t0 that can cancel out with each other. So all of this simplifies down to this right here. So now what I have is a simple form for my average rate of change between two times. Times t0 and t1. So that if I'm given two values of time, I can just plug into that and that will find my average rate of change. Okay, so what if we think of this a little differently of using that difference quotient format? So with that, we would use b of t plus h minus b of t over h. So b of t is given to us right here, but if I wanted to have a simpler form for b of t plus h, I could do a little side work first. So 32 minus 2 times t plus h. And we're going to go ahead and square that. So with this, we're going to essentially multiply. What I always recommend doing, because it's a very common mistake to turn this into t squared plus h squared, you can always just take a step to think of that as t plus h times t plus h, because what we actually need to do is FOIL. So we're going to multiply, 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 multiply. So we'll have t squared plus th plus another th, so that'll be a plus 2th, and then plus h squared. So that would be considered multiplying binomials if you need to look up anything for that. Or for short, we call it foiling. Okay, then I'm just going to distribute that -2 through, so 32 minus 2t squared minus 4th minus 2h squared. Okay, so all of that mess is the equivalent of b of t plus h. And then 32 minus 2t squared, equivalent of b of t. So I did all of that so I can make substitutions here. So for b of t plus h, I'm going to copy in 32 minus 2t squared minus 4th minus 2h squared. So all of that was to replace b of t plus h. And I'm going to go minus, and then in parentheses, b of t, which is 32 minus 2t squared, all over h. Okay, so we're subtracting the things on the right away from the things on the left, so I'm going to have a 32 minus 32, so that's going to make a nice cancellation. I also have a -2t squared minus a -2t squared, so those are going to turn into a 0 as well. So really all I have left over is a -4th minus 2h squared, all over h. And now I have a common factor of h that I can cancel out. If it helps to see this in the numerator, we can factor out an h. So we have a -4t minus 2h left over h, and those h's are going to cancel. And with that, it all lands at just -4t minus 2h. And what this is going to do is it's going to find the instantaneous rate of change. Or rather, how do I want to say this? Let's call it difference quotient at t with distance of 0. Or sorry, with distance of h. So the 2 points that we're working with here is that we're starting at t, and then we're landing at t plus h. And then up above here, our interval was having 2 distinct times. This one, it's like we only have one time, but we have our starting time, and then we have how long was it till the next time. Okay, with that, let's see these in practice. Again, 2 formats, but accomplishing the same thing. So using the formulas that we just found, let's look at this rate of change across 1, 3, and 3 and 3.5. So for 1, 3, for average rate of change, and what we just found is for average rate of change, we can calculate that with a -2 t1 plus t0. And that is to find average rate of change from t1 to t0. And then for the difference quotient, we call that dq, that was a -4t minus 2h across some value t, and then we just need to think of our second time as t plus h. So for the 2 times 1 and 3, we can use that first function. So for average rate of change, I would just go -2, 1 plus 3. And in that case, it would be -2 times 4, so that's a -8. Using the difference quotient, I need to rewrite this a little bit, because where I have 1, then I need to think of my second coordinate as 1 plus, and if I need it to be equivalent to 3, I would think of it as this distance of 2. So I'm working with a value of 1 for t here and an h of 2. So I'd go -4 times t of 1, and then minus 2 times h, which we're saying h is equal to 2. So -4 minus 4, and it gives us the same thing out. But we're just phrasing it as t and t plus h versus two distinct times. Okay, so if we're working with 3 and 3.5, then for average rate of change, we have our two distinct times. So I'd go -2 times 3 plus 3.5. So that's a -2 times 6.5, so a -13. And then if I want to use the difference quotient, I would think of this as 3 and 3 plus 0.5. So now I can see h is equal to 0.5 and t is equal to 3. So I would have, for my difference quotient, -4 times t of 3 minus 2 times h of 0.5. So -12 minus 1, so a -13. All of this to show how we set up thinking of our intervals, whether it's two distinct values versus one value and then the distance away to the second value. I know it's a bit of a weird way to say it, but with these two ways of thinking of the intervals, these are both calculating our rate of change as they occur around that value. So this one's just going that distance 1 to 3, and this is thinking of 1 is stationary, what happens when we're 2 away. And where we just want to keep going to that difference quotient idea, it's because we're going to start changing that distance. We're going to shrink it down to 0. So we look at what's happening as we have 1 and then basically 1. We can't be right at the same spot because our calculations won't work with that. But as we make h extremely close to 0, what's happening with these calculations? So with that, what if we wanted to evaluate what's happening at exactly 3? With these calculations, we kind of saw what's happening around 3, from 1 to 3, and then 3 to 3.5. We're getting pretty close there, but we want to narrow down what's happening right around. And essentially, we can use both of these as our calculations. What I'm going to do is show you how to set these up in Desmos to fill in the table based on which scenario you want to look at. So average rate of change, at the base of it, it's the difference in those two outputs at those two different times. And for the difference quotient, it's the same idea, but it's more having a single time with some distance attached to it, minus that output at the time, and then denominator of h. So with these, we're setting our time to 3. We want 3 to be stationary. And then as we look at average rate of change, we're looking at, okay, 3 to 2, 2.5. So what we're doing is we're making this distance smaller and smaller by choosing values for t1 that are getting closer and closer to 3. And then we look above as well. For the difference quotient, it's more about this distance. So we're at 3, and then like this is 1 below, 0.5 below, 0.25 below. So it's this distance that's shrinking down to a distance of 0, and then we look a little above as well. So over here, we're kind of converging on this idea of a t value of 3, and over here, we're converging on this idea of h being 0. As a distance away, we're closing that distance down to 0. And what we want to do is see how are those average rates of change behaving and what are they approaching from both sides. And then same thing with the difference quotient. And what should happen here is we should be getting the same values out. Okay, so going to our notation here for average rate of change, T0 is set. So what we're going to do is the output at T1 will be changing based on our value, but what we'll have is we'll always have 3 as our output on that right-hand side, and then we're subtracting 3 in that denominator as well. So 3 is set there, and then similarly for our difference quotient, we'll have B of 3 plus h minus b of 3 over h. So h is the only thing that we really need to plug in. Okay, average rate of change. Let's go into Desmos and have it do all the work for us. So what we can do with Desmos is we can set up our function. So I can call my function f of x, and that's going to be a 32 minus 2x squared. Set up my function. There's f of x. We can even look at a visual of it as we go. Now what I want to do is create a table. So what I'm going to do is there's this little add item function up here, and we can add a table. And what I'm going to do is 3, even though this table is showing 3, that's not an interesting part of our table. 3 is staying put, so we don't need to input 3 each time. Instead, I want to input these values for t1. So I go 2, 2.5, so on and so forth. And I actually have a screen that's all ready to go where I've plugged those in. Now what matters is how I defined my outputs. And what I'm going to do is I'm going to go ahead and erase y1 here. And this is a piece you want to pay attention to, and there are some questions in the online homework where this can help save you some time if you create these tables within Desmos. You can always calculate them by hand as well, but I'm just trying to show you some cool technology to do this. So what I can do is create a fraction, and then what I want to do is look at the function output when I've input these values for x1. So what I'm going to do is go f parentheses, and then on my keyboard I'm just typing x1. I didn't do anything special, it automatically made it a subscript there, so I just typed x1 and it fixed the formatting for me. And I'm going to close parentheses. So that's going to plug in our t1 value, and I'm going to subtract away f of 3. And then in the denominator, we're going to take that x1, and I'm going to go minus 3. And I paused there because the numbers aren't what they should be, and that's because I had a typo, and maybe you were all screaming it at home, but there it is. Okay, perfect. So now we can see our average rates of change approaching -12 from below and from above. So with that, we get an idea of our average rate of change getting closer and closer to -12, which suggests that our instantaneous rate of change would be 12 when we're at t equals 3. For the difference quotient format, we can do the same thing, but we would just set up our table a little differently. Okay, pause the video there so you didn't have to see me typing it all in. Again, we're going to set up our fraction, and that in the numerator, we're going to have our output at 3 plus h. So what I'm going to do is go f parentheses, and then we're going to take 3 plus, and then our value for x1. So I'm typing plus x1, close parentheses, and then we're going to subtract away f3, and then we're going to do all of that over our value for x1. And with that, we can see that same approaching of -12 from below and above. And with that, we can see how our instantaneous rate of change comes through. So this is the format that we're moving to with thinking of these. And with that, with setting up our function in Desmos, if you know your value for t, you can plug that in both spots, and then you just have to have your inputs changing for the values of h. And with that, we're plugging in h as our x values. So just in case you need it, the format we used is if we set up our function f of x, then to set up our difference quotient, it came through as f of, and in this case, we used a 3 plus x1 minus f of 3 over x1 for the outputs of our function. The value of 3 might change based on the question you're working on. The function will change based on the question you're working from, but that can give you a structure to use. And with that, we get an idea of our instantaneous rate of change for a function. And with that, using our average rate of change or difference quotient as a basis there. So this video, lots of notation, but but just to kind of get a practice at that idea of moving from average rate of change to difference quotient, but how it's accomplishing the same